Hi, everybody. Thanks for joining. Today we have Angie Chen from NYU. She is presenting on training language models for natural language feedback. She's a rising fourth year at NYU, advised by Kyung-Yoon Cho, and broadly interested in two directions of research: online training of LLMs from human feedback and evolutionary strategies, and understanding the learning strategies and training dynamics of LLMs. She's previously interned at Google Brain and Research on applying evolutionary algorithms to LLMs for neural architecture search and streaming disfluency detection. Prior to NYU, she worked at Google Search and on developing neural semantic parsing algorithms with the Sung Lab at Princeton, where she did her undergrad for ML applications to healthcare. I encourage everyone to leave their camera on just for the purposes of making it more interactive. And Angie said you can ask questions during the talk. Yeah, so take it away, Angie. Thanks for joining.
All right, great. Thanks so much for having me. So as Alex mentioned, I'll be talking today about training language models from natural language feedback. And this will actually cover two different papers, one of them more focused on code generation and the other one more on text summarization. But I'll start talking first about like the high level approach and rationale for it. And yeah, of course, feel free to ask questions throughout. I'm not really looking at the chat because I'm looking at the slides right now, so feel free to just like shout out. Yeah. Okay. So, as you all probably know, actually, like language model pre-training is traditionally offline in the sense that the pre-training data is collected prior to training and it doesn't involve any interactions between the language model and the environment. And it's also off policy, so meaning that we're learning the task independently of the agent's own actions. So again, no interactive guidance based on the language model's own outputs. So without these types of training schemes, it's a little bit more difficult to target the model's current weaknesses in its given environment, right? So there's some current work that attempts to solve this with schemes like RLHF, reinforcement learning from human feedback, but the preference data for that typically provides only one bit of information per pair of model outputs, right? Because the humans are just rating like which output is better. So instead, we're proposing learning from natural language feedback, which is a richer and a more expressive form of feedback than preferences. And we also think that this is advantageous because it's process-based rather than outcome-based. So it provides supervision on like why the model output, like why and how the model output needs to be improved rather than merely just focusing on the output. And there's a little bit of past empirical work actually showing that process-based feedback can in general be more effective than outcome-based feedback. And of course, natural language feedback is also more natural for language models since they are trained to intake language. Yeah, and there's a little bit of evidence showing that language models can incorporate natural language feedback at inference time. So like this image on the right, this is from the Codegen paper, the first Codegen, not the second one. And in it, they show that if they provided at inference time feedback, like in one piece of feedback at a time, Codegen was actually capable of incorporating that feedback into its code. And also our algorithm, as you'll hopefully see, is relatively simple compared to RLHF, and it doesn't require like an extra reward model or extra RL optimization algorithms like PPO. Okay, so I'll start out with some preliminaries. So our problem setup, we have a pre-trained language model. I'll refer to it throughout this talk as pi theta. There's a refinement model, pi refine, and we basically assume access to such a model in this paper, but we do also like illustrate like how we actually implement that on our own. And what this model does is it incorporates natural language feedback into an original model output. So it basically comes up with a revision or a refinement based off of that feedback. So we have some reward function R, it's just scalar valued, and we assume that this is usually non-differentiable. We have a small pool of human annotators, and our general goal is that we want to fit pi theta so that it can approximate a target or ground truth distribution. So I'll call it pi star. That fulfills this property that the probabilities output by a pi star are proportional to this Boltzmann distribution, where the exponent is the reward for any given task t. Okay, so I'll go through first a little bit this high-level algorithm, and then we'll delve later on like deeper into the details for each of the tasks. So to start out with, you have your pi theta, right? It generates multiple outputs for a given task. And then we ask our human annotators to give natural language feedback about the model outputs. And remember, this is usually done with very, very small samples of data because we know in general, human feedback is pretty expensive. And so in our very first version of the paper, we actually wrote this feedback ourselves. But as you'll see later on, we ended up scaling up to and using Surge AI instead. But part of like the appeal of this algorithm is that it should work even if you only have like a very small sample of natural language feedback. And next, we have PyRefine generate multiple refinements per output that incorporate the feedback into the original model outputs. And lastly, we use the high-quality refinements to fine-tune PyTheta. So that's the general high-level algorithm. Any questions about that before I get a little bit more into details?
Oh, may I ask, is the goal to replace step 2 with a model at some point?
Step 2, yeah, so there are works that attempt to do that actually. As you'll see in some of my analysis, the models we were working with at the time didn't work great at providing the type of detailed, correct feedback that we wanted. So I'll show you some examples of like model versus human generated feedback actually. But of course, the pace of language model progress is constantly accelerating. So who knows, we might have language models that can do this in the near future. And there's some work from Anthropic called constitutional AI that does explore this, but not with these particular goals. Okay, cool. Moving on then. So a little bit about whether or not this is theoretically justified, because I know like a lot of language model training schemes nowadays can feel like kind of hacky. So we did try to provide a little bit more of like a grounded justification for why this works. So let's say that you have a task T. So T might be like a document that you need to summarize or a program that you need to generate. It comes from a task distribution, POT, and we have this reward function that I mentioned before. And this is the same goal as before. You want to get our PyTheta as close as possible to your target distribution. Okay, so in order to get our PyTheta as close as possible to the target distribution, we essentially need to minimize the KL between those two distributions, right? And that's actually equivalent to minimizing this following cross entropy loss that you have here in the last line. And you can actually just move from the second to the third line because we just removed the term that only had pi star t in it because we're only optimizing data. Yes, Andy, I think that's correct. Yeah, it's very similar. Yeah. Yeah, so the problem with this is, of course, pi star sampling from pi star is kind of intractable. So how do we get around this? So instead, what we can do is importance sampling. And what that means is that we're going to attempt to assign higher weights to higher quality outputs. And so we're kind of like shaping the distribution towards what we want it to be. And so this like shaping of the distribution is sometimes known as a proposal. And so how do we actually define what the proposal distribution is in this case, we use feedback and we can actually approximate it. And this is derived from basically just the probability chain rule from like originally the joint distribution. So essentially we're using an empirical approximation of the marginalization of this proposal distribution over all pairs of possible feedback and the original model output. And I will explain a little bit more what each of these terms means. Yeah, so the first one is just the probability of the original model output for a given task. And that is something that we can very much sample. Next term is the probability of the feedback given the original model output that we're sampling from by just asking our human annotators to generate the feedback for us. And then lastly, we have this term that represents the probability of the refinement given both the feedback and the original model output. And so this is sampled from PyRefine. Okay, any last questions about that before I move on to the code generation portion?
Hey, I've got a quick question.
Mhm.
So can you go back one to the PF given x0?
Yes, let me.
So this is.
Oh, yeah.
Yeah. So that is the feedback, and then you just sample from you get the probability from the model of that feedback.
So in practice, we don't actually need this probability, right? Because we're not computing the probability of like Q itself, which we just need to sample from this distribution.
Okay, interesting.
Yeah, so it's a little bit confusing, but yeah, we're just sampling feedback from our annotators who are given the original model output.
Okay, cool.
Could you go over what P-refine was again? Sorry.
Oh, yeah, of course. That is just any generic model that can intake both the original model output from PyTheta and a piece of natural language feedback. And it generates something known as a refinement, which basically incorporates the feedback that was given into the original output. So it's supposed to give kind of like a revision of the original output. Okay, great. Any other questions? Okay, cool. So let's talk about code generation. That's my favorite part. So this is covering one of our papers, improving code generation by training with natural language feedback, with co-authors Jeremy Tomek, John Anders, who I think is here actually. Hi, John. June, Sam Bowman, Junyun Cho, and Ethan Perez. Okay, to start out with, I'll describe a little bit about like the tasks that we're tackling. So we used a mostly basic Python problems dataset, which is almost 1,000 Python programming tasks that are designed to be solvable by entry-level coders. So there's an example of this on the left side. And they also come with 3 unit tests. So because this data set, sometimes the natural language task description is actually a little bit ambiguous. So what we did in this paper is we provided one of the unit tests as part of like the description or the prompt. And then the other 2 are held out and used for evaluation. Yeah, so this is not a perfect training scheme. I do wish that we had like more unit tests or more evaluation, but for our purposes for now, it sufficed. And we also used the Codegen 6.1 B model. We selected this one mainly because it was one of the best open source models available at the time, and it actually demonstrated pretty similar human eval scores as Codex 12b, which is pretty impressive. Yeah, and this table below just sort of gives you like a little view into what its initial performance was on this benchmark. So this is 0 shot. The pass-at k value basically just estimates that in a given group, if you're sampling multiple generations from the model, in a group of k generations, what is like the expected number of them that will be, what is the percentage of the time that like an expected number of them will be correct. Yeah, so we have 31% and 63% for k equals 1 and 10. And then we also have this separate metric that is like of all of the generations that we have, which we also always generated 30 generations, like what is the percentage of the time that at least one of them was correct. Okay, so to collect feedback, so the annotators were instructed with 2 specific things. Number 1, they needed to describe what was wrong with the code sample, and number 2, how it should be fixed. And we also instructed them to not use any like entire lines of code. They can reference individual variable or method names, but that is like the extent of the amount of code that is allowed in the feedback. Yeah, so this is an example. This is actually kind of a fake example because the real feedback examples we have are often too long, and the code samples are also pretty long, so they don't really fit on slides. But this gives kind of an idea of the type of feedback that we collected.
Why the restriction on ability to reference code? Just it would make it too easy.
Yeah, we didn't want the model to just directly copy the code in the feedback, especially because our like longer term goal for ILF was for tasks where providing feedback is easier than providing the refinement. So you can imagine, for example, a case where like you're working in a really large code base or like with really long complex pieces of code where it might be easier to say that like, no, this sort algorithm is wrong and needs to be like more efficient, like maybe like, I don't know, use a data structure other than a list to sort. And then that might be an easier piece of feedback to give than like rewriting the code yourself. Okay, so the next part, generating refinements. So we have PyRefine. It uses the original code and the feedback to generate the refinement. So here's an example. So we know that the original generated code was wrong because it didn't pass all the unit tests. And the human annotator gave the feedback that the list variable was sliced incorrectly. And so the refinement basically just like adds this slice. Generally in our real data, we usually have like many more bugs than this to address in the feedback, but it's just an example. Okay, lastly, we just fine-tune PyTheta, as mentioned before, but we only use the refinements that pass the unit tests. Okay, so we compared ILF between various different baselines. So first of all, we compared ILF against fine-tuning on two gold standards. So two gold standards here that we considered was the MBPP gold programs. So MBPP, the data set comes with like gold, like correct programs. And then also we had asked our human annotators to provide their own refinements just so that we have like a basis of comparison, even though those are not actually required in the algorithm itself. In general, oh yeah, and then we also compared against zero-shot inference and also learning from Instruct GPT generated feedback and refinements. Okay, so compared to the, in general, ILF outperformed most of the other methods, but performed somewhat similarly to fine-tuning on human-written refinements, which I think is not unexpected because human-written refinements should be like basically your gold standard. Yeah, and ILF does outperform fine-tuning on MBPP gold programs on the pass at 1 metric specifically. It yields like 14% absolute and 3% absolute increases in the pass at 1 rates. And in a field like software engineering, that's actually really important because if you want like autocomplete in your IDE, for example, like you don't really want to have to sort through like 10 different completions and evaluate yourself whether or not which one is correct. So the pass at 1 rates here are particularly important, in my opinion, for applications. So, sorry, did somebody say something?
Well, could you explain the difference between MBPP gold completions and the human refinements?
Oh yeah, so yeah, sorry, it was a little confusing. So when we recruited human annotators to provide feedback, we also asked them to write their own refinements of the model code. And that's a little bit different from the MBPP provided gold code because as you can imagine, there's many different ways to write a correct program for the same task. And the annotators were asked specifically to revise the original model output. And they were instructed to not only incorporate their own feedback, but also to make only the minimal edits necessary in order to make the code correct. And I'll talk about this a little bit later. Something that's interesting about that is that those refinements are probably much closer to the model's original outputs than the MBPP programs are.
So is it not kind of surprising that like training on the gold standards does not beat the zero-shot performance? Or like only marginally does so?
Right, yeah, so that is surprising. And I was actually going to talk a little bit about this.
Oh, sorry.
Yeah, no worries at all. I'm glad that like this stuck out to you too. Yeah, so we do think that like that is probably because MBPP is like maybe a little bit like out of distribution, especially with such a small training data set, because we controlled all of the experiments here so that like we're only training on the same number of examples for each experiment. So that wouldn't be like a compounder. And so that means that because we didn't have that many like refinements, that means that we only sampled from the MBPP gold program. So probably if you fine-tuned on like the entire MBPP gold program dataset, like you would probably be able to do a lot better. But here, like you have a set of programs that are probably a little bit out of distribution in comparison to what the model itself is already generating. And so it's probably harder for it to learn with such a small data set.
Yeah, and really the MBPP gold programs, they are a mess. Like they're very weird. They're very weird because they're automatically generated. So most programs will look something like T1 equals T0 plus 4. T2 equals 2 times T1. So they're very weird, which, yeah, as you were saying, like they're very out of distribution. Unless you train your model on very weird code.
Yeah. And in general, I think a lot of code benchmarks, like the gold code that's provided is like not always very high quality. So
good to know. Cool. Thanks.
But yeah, we can dig a little bit deeper into these sources of training data. Because yeah, I did notice this as well, that merely training on just a small sample of the MBPP gold programs didn't make a significant difference in accuracy over zero-shot inference. And so, as I mentioned, that might be out of distribution. So one thing we looked at is, what if you calculate the perplexity of the MBPP gold programs, the pi-refined generated refinements, and the human written refinements, but using the pre-trained Codegen model? And so, as you can kind of see here from the blue bars, there are some higher blue bars to the right of the histogram. That means that the MBPP gold programs, according to the pre-trained Codegen model, are like higher, has more higher perplexity outliers. And so like this does indeed seem to be a little bit out of distribution compared to these other two data sets. So that means that it's likely easier for this Codegen model to learn from the orange and the green data sets, since they're closer to Codegen's like own original distribution before fine-tuning. But that's really interesting, because that says a lot about like what kind of training data is helpful, because these are all programs that are considered to be functionally correct, right? But they just have different styles, and a couple of them are much easier for this model to learn on than others. Okay, and what I thought was really cool, I think somebody already anticipated this particular analysis, is we wanted to see like how much can model feedback yield the same benefit as our sample of human written feedback, because human collected feedback is great, but it's so expensive and generally difficult to collect. So we randomly selected K tasks from the set of MBPP tasks for which Codegen didn't originally output a correct answer, and prompted InstructGPT to generate both the feedback and a refinement. And so that's what we're comparing here with the purple and the magenta lines, or the solid lines, basically. The dashed line here is the zero-shot performance, and then the black X represents the ILF performance. And so like even if you continue to increase the number of InstructGPT generated like examples of feedback and refinement, the rate of improvement is still much slower. And then like at least for this number of K, it never actually ends up reaching the ILF performance. And the reason that we had to keep K like basically like maxed out at 200 is because we only were using original tasks for which Codegen had not generated any correct outputs. So we are limited in like the number of examples we have here. Yeah, but of course, again, language models are rapidly improving in quality, so we do expect this gap to narrow. But for like a qualitative analysis of like what was actually going on here, I do have some examples of like differences between like model and human feedback. So for this particular example, the InstructGPT feedback is not correct or relevant, because we specifically asked for how to fix bugs or how to make it correct. And this InstructGPT feedback is attempting to address efficiency rather than correctness. Versus basically our human feedback was like always correct. Okay, so another example. Sometimes what we noticed really often was that InstructGPT would just simply restate the description of the method instead of providing feedback, so that's really not helpful. And so finally, I think we had a number of takeaways from this paper. In general, we showed that like ILF, even though this is kind of a smaller scale study, we have a larger scale one following up right after this. It can significantly improve the quality of a code generation model, even with just a small sample of natural language feedback. It's not model specific, and it provides an online training signal. And ILF can be thought of as a method for generating training data that's closer to the model's original outputs and data representation space. And that specifically represents the kinds of bugs that the original model generates. So it's like a very targeted method of training. But of course, there are some limitations. It is overall meant to be a smaller scale proof of concept study. And we didn't really get the chance to study what would happen after multiple rounds of like feedback or with multi-turn feedback. In general, we discovered the hard way that annotating code data is also very expensive. And also, this in general only works if you have access to a sufficiently powerful pi-refined model. Okay, so that's it for the Codegen side. I'll move on to summarization next, but are there any questions here?
Could you talk a bit about like the code annotation experience? Like we certainly think about annotating data a lot. What were like, what is like the process? Like you just ask Surge, or I guess you guys wrote feedback in this case. Is that right?
So in our preliminary studies, we did write the own feedback, but then what is finally represented in the paper is from Surge feedback.
Okay.
I think what I found from like the annotator experience is that code data is pretty, well, language data is difficult to annotate too, but with code data, what we encountered a lot of the times is that sometimes annotators won't actually check if their code is correct unless you explicitly like make available like an interpreter to them and like tell them explicitly you have to check that this is correct. And also another interesting thing is that you have to like people write code very, very differently. And so when we were trying to get them to write refinements that were not too far from the original model completion, it took us a couple of rounds to get that correct. And we had to use like edit distance to check and everything. In some cases, the annotators said they actually found it a lot more difficult to create that like minimally close correct implementation than just reading the code themselves. So
is the feedback stylistically really varied, or is everyone forced to write in like complete sentences and like have certain code style, or I don't know, are there like particular formats or guidelines that make the feedback better?
Oh yeah, so for the natural language feedback, we didn't actually enforce very many constraints on style. So I didn't say like, oh, you have to have complete sentences or anything like that. We really only enforce those two requirements that I mentioned, that it has to mention specifically what is wrong and how to fix it. And there was a variety of lengths as well, especially because, and we have further analysis of this in the paper that I didn't mention in this presentation. There was actually even feedback that had to address like 4 or 5 bugs at a time, even though these programs are generally like not super long. And so sometimes the feedback would end up like varying a lot in length depending on how many bugs there were to address.
Yeah, I just had a small question. What happens if the refinement like model or policy is the same as the original model that you're trying to tune? Can that work? As like what I could imagine is maybe the model knows how to take in the feedback and then write a better response. It just didn't realize it from the original prompt. So less so making errors, but more like maybe a stylistic feedback.
Yes, yeah. So we're actually trying to explore this in a like follow-up study that I'm contributing to. I think it's an open question of like whether or not like does your PyRefine model need to have like more capacity or can it have less capacity? And it probably differs a lot depending on like whether or not the model was like instruction tuned, for example. But you're right that I think we have seen this phenomenon where the model didn't originally generate the correct output, but once you give it feedback, it can generate the correct output.
Yeah. That one equation you showed with the 3 like components to it, like the marginal probabilities, I just noticed like if we set the 2 models to the same original model, I wonder like what mischief would go on the math side. But either way, it's a pretty cool direction.
Thanks. Yeah, I don't know. I would have to work the details out on that one, but I think we're trying to explore that in like a follow-up study more generalized across domains and data sets. Okay, cool. So summarization. All right, so this is actually led by my co-author, Jeremy. And we also wanted to explore summarization because it's markedly different from Codegen in many ways. There's not as precise a ground truth as functional correctness, which you have in code, and human evaluations tend to be the gold standard for a task like summarization, but even those evaluations are noisy. So you have this extra problem of like, how do you select high quality refinements? We would hope that PyRefine always generates high quality refinements, but that's just generally not the case. So we wanted to see how well ILF could be adapted for a task such as this, where we don't have that additional signal of like passing unit tests for selecting both the best refinements and the best final samples. Okay, so I wanted to give an example of like how we collected feedback. So the annotators were asked to give feedback about these multiple different attributes. So essence is like does it basically describe like, is it a good representation of the post? Oh, and this is from the Reddit summarization data set that was originally introduced, I think, it was adapted from, Steen in 2020 had adapted this original Reddit summarization data set. So clarity, is the summary reader friendly? Does it express its ideas clearly? Accuracy, is there anything false in it? Purpose, does it have like the general same like idea of like what it's the main message that it's trying to get across? Is it concise enough? And is the style similar to the original post? And so this is a real example here. I did cherry pick this one because I wanted one that was short enough to fit on the slide. So this is one of the shortest ones that we have, but they're generally much longer than this. Yeah. So in this case, the annotator gave the feedback that the summary isn't accurate because it didn't mention that the poster's girlfriend got blackout drunk and cheated on him. Okay, so for the general high-level algorithm, so it's somewhat similar, but with a few tweaks. So we actually generated our refinements this time not through a separate fine-tuned model, but through zero-shot prompting of DaVinci 001, because we found that it was, in general, good enough. And the instruction was write an excellent summary that incorporates the feedback on the given summary and is better than the given summary. So to evaluate the like reward of each example, where if you recall in Codegen, the reward is basically whether or not it passes the unit test. But here to do that, we actually use an instruction-tuned InstructGPT model. We prompted it with the question of whether the refinement incorporates the feedback, and then we took the probability of the yes answer. And that's averaged across 5 different prompts. And we compute that for each of these 5 refinements. So then we selected the refinement that had the highest average score. And in the paper, we actually referred to this like refinement, like selection/ranking process as instruct-RM ensemble. And so that like highest ranked refinement is then used to fine tune. Okay, so this plot is comparing a few different things, but let's first look at just comparing just the fine-tuning algorithms. So first, we want to compare ILF against both fine-tuning on the initial summaries versus fine-tuning on human-written summaries, which were collected for our human annotators. So initial summaries I'm talking about is the Reddit summaries, and then we have fine-tuning on the human-written summaries, which we collected ourselves because we determined that this was actually like a higher quality baseline than the Reddit summaries. Yeah, and so ILF does outperform both of these, and it also outperforms simply just sampling from DaVinci 001, which is this brown line at the bottom. Okay, but what if you actually want to compare ILF to learning from binary preferences, which you can consider to be kind of a standard approach from learning from feedback, because that is essentially the approach that's used in RLHF. So one way of learning from binary feedback is to train a reward model and use it to do best of n sampling. And that's been shown in the literature to often be competitive with RLHF. And so that's why we take that approach instead of tuning RLHF ourselves, because that is quite the black box that most of us don't quite know how to do that well currently. Yeah, so to train the RM, we first fine-tune an OPT13B model to classify whether a summary is high quality or not. And then at test time, we generate 64 summaries using the ILF trained model, and then we rank it based on the probability of, rank the summaries based on the probability of being a high quality summary according to OPT-RM. Yeah, so to look at the results. Okay, so now we're comparing against 2 different methods here. We have the methods where OPT-RM simply just does best of n sampling from the original. FEME is the same thing as like DaVinci 001 here. We're just using OPT-RM to do best of 64 sampling on it. And then the last bullet here is ILF combined with this technique. So the summaries are generated by an ILF trained model and then filtered and ranked by OPT-RM. So as you can see here, that's the pink line compared to the green star. And since the y-axis is like win rate versus human summaries, that tells us that basically the combined method, where we're combining ILF with learning from binary preferences, actually outperforms everything else. So that kind of suggests that both methods are independently learning valuable information about human preferences and that they can be cumulatively helpful when used together. Okay, and to talk a little bit about like future directions. So model-generated feedback, as we talked a little bit about earlier, maybe we don't necessarily need human written feedback, and there's a little bit of work on this already. It's often referred to as constitutional AI, and it's from Bai et al. And there's also this self-refined work, which explored a similar scheme with model-generated feedback on a variety of other tasks like acronym generation, common sense generation, code readability, and so on. And of course, I think some interesting future work that could be done on this is also how you can generalize this approach across multiple tasks and domains, because here we did specifically adapt the reward function and the refinement models for each task and data set. And that is, it does take some tweaking and generally more labor than we would like. So it could use improvement on this front for sure. Okay, thank you, everybody. Let me know if you have any questions. And if you want to reach out, my email is here, and I provided the archive links of both of these papers here. Okay, I think there are some hands raised. I don't know how to tell who's.
Well, there's a classic problem of trying to clap and accidentally raising your hand.
Okay. Yeah, thanks so much for having me. And I'd be curious to hear if anybody has any like thoughts or questions in general.
I can lead off with a question, and I'm gonna go back to the kind of feedback aspect again.
Yep.
I'm curious, like, one, if you can get a sense of like how much feedback costs for you guys. Like, did you search also for this portion, or?
Yes. Yeah.
Okay. Can you give a sense of how much it costs, and also like, I guess I want to try to get a sense of is like how much time should I invest in a single piece of feedback? That might be like, should I go for one really long detailed piece of feedback, or like really short and quick and just get a lot of data?
Mm-hmm.
I'm curious if you have experiments or insight into this.
Yeah, okay, so for the cost, I only remember off the top of my head the cost for code annotation, which was, I think it was like $23 per sample, which is quite a lot in my opinion. And it actually took them an average of like 27 minutes per sample. So it's quite laborious as it turns out. But I guess the good news is that you don't need like a very large sample of that feedback in order to, you know, make significant improvements. And I'm hoping that in the future, this will also become more streamlined and cheaper. As for shorter versus longer feedback, I think with Codegen, we did observe that it was fine if the feedback, 23 bucks per second. Yeah, I know, right? Yeah. Yeah, we did observe, at least for code, that like it's fine if like you're not using complete like long sentences, so long as you're just hitting all of the bugs that need to be addressed. And John, I don't know if you might feel like you can comment on like the summarization feedback.
So I don't have the numbers of the money on top of my head. I was checking the paper right now, and it said that the dataset collection was like 40K. So we have 5K annotations. So yeah, it's just doing the math, I guess.
So how much was the total?
40K, but we were like gathering gold summaries, feedback, and also preferences. So they were doing the 3 tasks at the same time because we wanted to have like the same data for all the examples in the summarization data set. And also we were like checking how costly it was in terms of time for the annotators to give like feedback versus binary versus the gold. And we found that like giving the gold summary versus giving feedback was like really similar in terms of time that for the annotators. So I guess that we had in our minds the idea of like having a task that is much easier to give feedback than to solve it. But I guess that summarization wasn't one of those. So yeah, it was like similar in terms of like time cost for annotators to give like the feedback, natural language feedback, or to give the gold summary.
I think for Codegen in total, we spent only like $7,000 to $8,000 because it was a little bit more. We had different sources of funding, so Codegen was a little bit more of an academic source of funding. So that's what happened there. Andy, what you were saying about, I'm actually surprised that radiologists only got $100. I thought they would get more. So,
it's something insane.
Yeah, that is pretty wild. GPT learned how to respond to my monkey level feedback. Why chart sideways? What was that feedback to?
Like just conversing with it as you code, it can somehow handle like pretty poorly constructed feedback.
Yeah. So a lot of models nowadays are pretty good at like, I guess, doing what you want it to do. But when it comes to actually analyzing whether something is correct, that's a little bit harder for these models. Sorry, there's a raised hand. Claire, do you have
Hi. So I work on the human data team here at Cohere. I just have some questions. Like, what was the background that you saw amongst the code annotators? And did you feel like they had to think a lot about the feedback quality and data validation steps?
So a lot of them had, I think, like some software engineering experience because you can code, then why not, right? Sorry, what was the other question?
Like, did they have to think a lot about feedback quality and data validation?
Yes, definitely, because I think we actually did in total maybe 3 rounds, and we didn't use the data from the first or the second rounds because it just actually wasn't high enough quality feedback. So as I mentioned, we had to go back and iterate with initially. Sometimes the feedback would just be like, oh, like we're just going to show you how to write the correct code, but it's going to be completely different from the original code. Or annotators would just describe what was wrong, but not how to fix it, or how to fix it, but not what was wrong.
Classic.
Yeah.
Cool. Thanks.
Do you guys are just like manually reviewing a lot of the feedback too?
Yeah, for the first 2 rounds. And then for the third round, Surge actually did help us a lot with this. So I consider that as like part of the overhead of the costs, because I think different annotation services are quite different in terms of cost, that they were able to help us a little bit more with just communicating with the annotators so that I didn't have to constantly be like responding to annotator messages.
I was thinking with the code feedback project, you can look at like feedback or like what features of the feedback are correlated with more tests improved as a way of proxying like the effectiveness of the feedback. Like the length of the question, or like, I don't know, like if they give you specific like mentions of parts of the code to fix, and then correlate that with how well that improves the models.
Oh yeah, that's a good question actually. So we have a breakdown of what types of feedback are provided, like in the paper of like, there's a lot of stuff related to like dynamic programming and arithmetic. And we also have an analysis showing that like the more bugs that are addressed in the feedback, the harder PyRefine, or the harder it is for PyRefine to generate a correct refinement. But we don't have that correlation, and that's something I would be interested in looking at for sure.
Had one idea, like what if you purposely got your annotators to like start with something that almost works but doesn't quite work, and then create the actual correct solution, and then get a different annotator to like give a feedback that would lead from this subpar solution to this right solution. But because it's easier to maybe make up a feedback that does that transformation. But then again, now you have annotators everywhere instead of a model doing the refinement. So
yeah. And I do suspect that part of the reason why this works so well is because you're not straying too far from the model's original outputs.
yeah, you're right.
Yeah, but that would be an interesting idea.
Okay. Well, you have Angie's contact info here, and thank you so much. This is super informative.
Thanks, everybody.
Thanks, Angie.
It was good chatting with you all.
Thanks.
Thanks. See y'all.